So sometimes an interesting thing can happen when you're dealing with total internal reflection, and that is it's possible to actually frustrate the refracted ray and force it to enter a separate medium. Typically this occurs when the gap between the two medium is very, very small. In the examples shown here, you can see the fingerprints on the inside of the glass where normally you can see a reflection is occurring. Same thing over here. We have a total internal reflection, but in this separate piece of glass right here, we have a slight transmitted ray going through. So just to kind of refresh what's going on here with total internal reflection, what happens is that if the refracted ray actually reaches an angle of 90 degrees, well, refraction can't occur back into the substance where it came from, and so the light ends up reflecting. What you can actually see is the reflected beam, which will frequently be fairly weak initially, will all of a sudden jump in brightness once you reach that critical angle, and that's simply because of energy conservation. All of the light that's going through here, in the initial case when there was some refraction, that light energy was being split between the refracted ray and the reflected ray. But as soon as you reach critical angle, there's nowhere else for the light energy to go, and then it ends up having to follow the refracted ray. Now, what happens is if you were to look closely somehow at the medium, or just beyond the point where the total internal reflection occurring, there is something called an evanescent wave. And what that means is the light field actually extends a little bit beyond the substance. It's a kind of a decaying field. It's not an oscillatory field. And we'll look at this a little bit more when we talk about waves of light. But the field is extending a little bit, but it decays and doesn't propagate. Here's kind of an example of what that looks like, where this is showing the field strength and that field is decaying. Now here you can see we're pressing two pieces of plexiglass together, and under normal circumstances this light ray ends up undergoing total internal reflection. But if the contact point between these two substances is less than a wavelength, it's possible for that evanescent wave to start oscillating again. And so that means that that light wave that's extending into their medium hasn't died out completely and can start oscillating in here. And so we have a little bit of light that's actually getting transmitted through. This is actually similar to the idea of quantum tunneling, where particles can actually tunnel through a region that they normally could not travel through. Now, one place you'll see this is in beam splitters. And so with these beam splitters, we have here two separate prisms that have a gap between them. And if you tune that gap so that it is roughly the wavelength of light that you're interested in, then you can control the amount of light that gets split between these two rays. And so you can have a beam splitter that perhaps splits the beam 50-50 or 70-30 or whatever splitting you want based on that gap between the two. Just a couple of other applications where you'll see total internal reflection. Sometimes multi-touch sensors will use this, and so you have a sheet of some sort of material, and then there's light that is being shown through the substance. It's actually bouncing back and forth between the surface of the substance, but if you place your hand on the surface, it will actually let some of that light leak through. And if you have a camera, you can actually detect those points, showing you where touch is occurring. Another example would be light boards, where again you have light that is actually transferring through the substance, bouncing off of the back face and the front face, and then if you go ahead and you write on the surface, that will frustrate that reflection and let through some of that light.